Welcome to mean value theorem and average value. This is a very practical lesson because we're going to be doing some application of some concepts we've been learning, our integrals, right? We're going to be doing some applications. I also like this concept because like position, velocity, acceleration, that lesson, this ties back to some things that we learned in the differential part of this class. And third, this formula is very intuitive, and how to work with this formula is very intuitive. So I think it makes it easier to understand when it's a very intuitive concept. And it's always and almost always an FRQ, so it's really important that we master it. So let's take a look at, we're going to start off with average value. All right, so here we have velocity, v of t, and we have learned that the area under this curve is the total distance traveled. But what's the average rate of speed for this trip? Right, so now I'm not looking at the average distance. Like we looked at area under the curve, there's total distance. I'm looking for average speed, the average rate of speed for this trip. Right, so I'm looking for the average of this integral here. So we know that the area is the total distance. We know the integral, right, is the total distance. So the total distance here is the area under the velocity curve. And what we find when we integrate the velocity function. Uh-oh, I'm running out of space. For some interval. Right? Oop. I did not mean to hit extend a page because it makes everything really, really small, and I still had enough room. There we go. All right, so total distance, the area under velocity curve, is what we find when we integrate the velocity function for some interval. Exactly this, right? Total time, that's just the change in time. So if we were to integrate and evaluate the velocity function and divide by the change in time, we would have the average rate of speed. Because all the average rate of speed is the total distance versus the total time. Right? Speed. So distance equals, rate equals distance. I was going to write distance divided by time, and that looks awkward. It looks better to go in this direction. Rate equals distance divided by time. Right? We just take our distance divided by our time. Right? And when we do, and what our distance is represented by integrating the velocity, we get not the rate at one moment, we get the average rate over that time period. Right? So another way we could write divide by our change in time is to write multiplied by 1 over the change in time. And actually that is our average value function. And this is the average not just of the velocity curve, but of a velocity function, any function at all. If we want to find the average, we find the total by integrating, evaluating, and multiplying by the change in x. And the change in x, notice, is always going to match our limits of integration. Right? So it's just the change in the limits of integration. And I believe you have this picture, this whole slide in your notes. So feel free to add in that information to give it a little context and help and have it make sense for you. Okay? So now let's take a look at finding the average value of some function. Oh, actually, let's look at the formula one more time, and then look at finding the average value of some function. All right, so the average value is 1 divided by b minus a, which is just 1 over the limits of integrations. You're changing x there. You're going to integrate and evaluate to get the total change. And that's all there is to average value. Right? Add those pieces of information underneath the formula so it helps, it gives it context. And when you explain something in words, a lot of times it makes the formulas a lot easier to remember. And this is one formula I think is very, very intuitive, right? To find the average, we're just taking the total over the change in the interval. That's all it is. All it is. So we want to find the average value of the function f of x equals 1 plus x squared on the interval -1 to 2. If we want to find the average value of that function, we have to find the total change in that function, the total change. And the total is going to be what we get when we integrate and evaluate. The average is what we get when we multiply by the change in x, which is going to be 1 divided by 2 minus a -1, your upper limit minus your lower. And we're going to integrate 1 plus x squared. Don't forget your dx. And this is going to be evaluated from -1 to 2. Let's simplify that. It's just 1/3. And we're going to integrate. And this is a nice, easy integration. So we have 1 is going to become x using a power rule. X squared becomes x cubed divided by 3. And we're going to evaluate that from -1 to 2. So we have to equals. We have to plug in the 2 and then plug in the -1 and subtract. So we have 2 plus 2 cubed divided by 3. Teeny weeny 2 there. And then we're going to subtract what we get when we plug in -1. So we have -1 plus -1 cubed divided by 3. So we have 1/3. 2 plus 8/3. Distribute the negative. Minus a -1 becomes +1. Minus, this is going to be a -1/3, becomes +1/3. Let's add these two together because 9/3 is 3. So we have 2 plus 1 plus 3, which is 6. So our function takes on many values between -1 and 2. The average of all those values is 1/3 times 6, which is 2. 2 is the average, right? So if you were to find which would be impossible, to find every value from -1 to 2, because there's an infinite number of values between -1 and 2, and were to average them together, it would be 2. Thankfully, we don't have to do impossible work. All we have to do is use our what we've learned about integrals, the definite integral here, evaluate to find the total area under that curve, and then multiply by the change in x to find the average. So the total area under the curve is 6. The average is 2. And that's all there is to it. Now we're going to, that's all, as a matter of fact, this is the only average value, strictly average value problem I have where we're just finding the average value because it's that easy. But we're going to apply average value or use average value as we look at mean value. So mean value theorem for integrals just adds a little something to average value. And it's not complicated at all. Promise. Matter of fact, this whole concept is only as complicated as the function that you have to integrate. We also, you'll see in the next video, some applied problems. The mathematics isn't difficult so long as you understand the concept of average value. And actually, instead of writing av there, which looks a little sloppy, I'm going to write average value, if you don't mind, before I change the page. Average value. So let's look at mean value theorem for integrals. Just as a reminder, and actually maybe I should put this on its own page. I think I will do that. This page is a little crowded here. Oops, and I want to clone the page. I try not to do these things when I'm recording because the smartboard doesn't really like it when I do this, so, or at least doesn't like it when I do it when I'm recording. And I took off too much there. But, well, I can't really pause my recording, and I don't want to start over. So you'll have to bear with me for a moment. First, I just want to remind us what mean value theorem was and intermediate value theorem was when we were, let me get rid of that 5 there, but I'm going to leave up, or we can just leave the 5 if it doesn't want to go away. There we go. All right, so just I don't want to get rid of intermediate value theorem, but I'll review that. So I'm just going to do this. There we go. All right, so remember, intermediate value theorem, there must be at least one time C. Actually, no, I'll go over that part. I lied. I'm going to go over that when I get to on the next page, because that deals with our specific problem. Let me just remind you of intermediate value theorem and mean value theorem from back when we were looking at, and I had it over here. I should just move this whole thing. No, of course it won't move. Let's see if I can just move this over and go over that. And I'm very sorry for moving things around during a recording, but I'm sure you'll forgive me. There we go. Right, so I wrote this on there earlier because I wanted to kind of review mean value theorem for derivatives, not have you get confused. And then I looked at the page just a moment ago and I'm like, I'm just a little busy. So let's give it its own page. There we go. So, little reminder of intermediate value theorem. Right? So, intermediate value theorem for continuous function, every value, right? So, if your function is continuous on some interval from a to b, and you get some value for f of a, and some b, and f of b is some value, well, every single number between f of a and f of b, there must be some x value that is equal to that y value between f of a and f of b, right? So, in other words, if I have some function here, come on, where's my picture? There we go. And this is, right here is a, picture's always worth 1,000 words here. And there's b, so right here, that's f of a, and right here, that's f of b, oops, f of b, right? So there's some x value between a and b such that y is between f of a and f of b. So if I were to find this point right here, there's some x value, right? Some x value, let's just call it c, right? Where f of c equals, and we'll just call this k, equals k, right? You can't skip over any values. If you're a continuous function, then every y value and every x value is represented. So for every x, there's some y. For every y between, we first saw a mean value theorem, oops, when we were working with derivatives. Okay. So if you're, just a little reminder what mean value theorem was for some interval, right? So the change in y over the change in x, change in the function over the change in x, which gives us the slope of the secant line, right? The average rate of change is the slope of the secant line. Our derivative has to be equal to the secant line somewhere, right? So at c here, whatever c is, f prime of c equals the slope of the secant line. In other words, our instantaneous rate of change equals the average rate of change for some value of x, right? If we are a continuous function. And I should say, so I'm going to add that for continuous functions, right? Because if it wasn't a continuous function, right, all bets are off, right? Can't use mean value theorem, can't use intermediate value theorem. There's nothing more we can say. We can't be sure, right? But if you're continuous, every value's got to be represented. So that was mean value for integrals because we were integrating. We were dealing with, mean value for derivatives because we were differentiating. Now we're integrating. Integration has its own mean value that applies to integrals. So let's take a look at that. Now we've had a little refresher course on intermediate value theorem and mean value theorem. Always good to have a little review. All right, so, and I'm just going to get rid of this because this is really not needed, but I'll leave that over there. All right, so I'm using the same graph of our trip. Let's say the average speed was 50 miles an hour. Right, so this is your average. So notice, sometimes we're below the average, sometimes we're above the average. Right? So wouldn't it be nice if, you were, say, going that speed, and the officer pulls you over? You could say, I was only at a moment. My average rate of speed, that was right at the speed limit. Yeah, that doesn't work though. They don't care about your average. All right, so this means sometimes our speed is less than 50 miles per hour. Sometimes it's more than 50 miles per hour. By intermediate value theorem, however, there must be at least one time when our speed was exactly 50 miles per hour. There could be lots of times, but there has to be at least one, and that's mean value theorem, and we're going to say for integrals. We have it for derivatives, and we have it for integrals. Right, so just a reminder, this is related to intermediate value theorem. For a continuous function, every value between two endpoints must be reached by some value of the function. So it's not like you could go 49 miles per hour and then go 51 miles per hour without ever going 50 miles per hour. It's just not possible. Right? At some point, you're going 50 miles per hour. We can use mean value theorem to find when. When were we going the average? Right, so mean value theorem, we're just taking our average value for our function formula, right? The definite integral multiplied by the 1 over the change in x. And now we're going to, so that gives us what, right? So when we have an answer, right, whatever that answer is, 50 miles per hour, 2, that was what the average is. We're going to add a little extra part to it and find out when. When was the average? When was, well, for what x value, right, was our function equal to the average? So we're just going to add one little piece to it. We got to find the when. Right? So this below here is just another way to write it. They mean exactly the same thing. So the f of c is the what, the c is the when. So c equals when. And that's what we're going to solve. Let's look at a little picture. All right, so here's our little picture. All right, so we have y equals x squared. The shaded region on the left has an area of the definite integral evaluated from 0 to 3 of x squared dx. Right? The change in x there, the intervals from 0 to 3. If we integrate, we're going to find the area under the curve, which is the area, the total area for that. Right? The rectangle on the right also has an area of the integral from 0 to 3 of x squared dx. Now, let's just show you that that rectangle really does have that area by integrating here our function. All right, so this is going to be equal to, all right, so we're just finding the total, which means we're just integrating. No average value here, just integrating. All right, so this would be x cubed divided by 3, evaluated from 0 to 3. Oh, excuse me. We want, well, yeah, right now we're just finding the, let me erase that extra dot there. Let's just find the total first. All right, so now we plug in. All right, so we have 3 cubed divided by 3 minus 0 cubed divided by 3, which is 27 divided by 3 is 9. Right? So 9 represents our total area. Our rectangle here also represents our total area of 9, or represents a total area of 9. Right? We can see that this distance here, even though it's not really the same, scale is not quite the same, but along the x here, the change in x is 3. You look at that and you go, that's 9? Yeah, it is, because our y scale is really different than our x scale. And that's just because the y values are larger than the x values for y equals x squared. This height here, our change in y, is also 3. And we know the formula for the area of the rectangle is 3 times 3. Excuse me, is the length times the width. So our area here is 9. So the area under that curve and that rectangle are exactly the same. They both have an area of 9. Right? So if we think of the rectangle's height as the average value, now why would that be the average value? Well, if we take 9 and divide it by 3, right, because so this rectangle was drawn to be the average value. Our change in x, let's take our change in our average value here. Right, so we know that the value, the total area is 9. The change in x is 3 minus 0. And so 9 divided by 3 is 3. Right? So 3 is our average value. And our rectangle here has a height that's equal to our average value. Because together, that height and our width here is going to give us 9. Right? So we have it perfectly drawn in there. So you can think of the rectangle's height as the average value of our function on 0 to 3. Right, so that means if we were to take all the different values and kind of smush them together and turn it into a rectangle, the average would be 3. Notice that somewhere my function is actually equal to that average, which is the whole reason the rectangle's there. So you can see that somewhere the function, the value of the function equals the average of our function. Okay? So if we think of the rectangle's height as the average value of y equals x squared on 0 to 3, because that height or function value is the same for all x on 0 to 3, then if we integrate and then evaluate, take the difference in the, divide by the difference in the x values there, we're going to have our average value. So the average value of function is just, the rectangle's height signifying the spreading out of all the various function values over the interval. So every location within the interval, the function takes on the same value. If we represent that constant value as y equals f of c, there has to exist some x value that makes this average value work. The mean value theorem for integrals assures us that such an c value exists, and we can, if needed, determine that value. So here we can kind of see, well, maybe it's somewhere between 1 and 2, right? If we solve using the mean value theorem, we'll actually can find where that value is. So this was just kind of a visual to help you get an idea of what average value is. You're just taking all the different values for the function and smushing them all together to make a rectangle, right? That gives us the average, right? So if we would add them all up, right, and made it so it was all equal, right, that would be our average. And somewhere our function equals the average. So hopefully that visual helped you. Oops. And I left this one up here. I'm like, oh, I didn't erase the board. I left this one up here because it's in your notes, and it seemed kind of pointless to erase it if it's already in your notes. So we want to find c such that satisfies the mean value theorem for f of x equals x squared on 0 to 6. Right? So now we're going to take the average value. We're going to find that. Right, so the average value, we integrate x squared dx and evaluate from 0 to 6 and multiply by that change in our interval, 1 over 6 minus 0. So that's 1, 6. We integrate, we have x, yeah, so here I'm solving the problem from the last page. Aren't I? Oh, no, I'm not. I'm sorry. This is not the same problem as the last page because my limits of integration were different. Same function, different limits. Oh, by the way, we can go back and solve that other one too. All right, so now I have 1, 6 x cubed divided by 3. Evaluated from 0 to 6 gives us 1, 6 times 6 cubed divided by 3 minus 0 cubed divided by 3. Well, that's just 0. So we have 1, 6 times 216 thirds, which is 72. So 1, 6 of 72 is 12. 12 is what? That is the average value of the function. Right? That's the what, and now we need to know the when. Right? So the what is the average value, that's 12. When does that occur? All you have to do is set that function equal to that value and solve for x. That's all there is to it. This one, if you don't mind being creative, a little bit creative, is a difference of squares, right? Because square root of 12 is a perfect square. Think about it, it's a square, right? So I could factor this as x plus 2 square roots of 3, right? Because the square root of 12 is 2 square roots of 3, and x minus 2 square roots of 3. I like to factor whenever possible. Right, so we have two values here. Make sure you choose the right value. Negative 2 square roots of 3 is a no. And why? Not because it's negative. Well, yeah, kind of because it's negative, but because it's not on 0 to 6. So if you're outside your interval, you're a no, right? So add to these notes here, C has to be on the interval. So in this case, you have to be between 0 and 6. So if you're not between 0 and 6, if you're less than 0 or you're more than 6, you're no, right? You're out. But 2 square roots of 3, that's okay. That is less than 6 because 2 times 3 would give us 6, and the square root of 3 is certainly less than 3. So C equals 2 square roots of 3 is when that occurs. That is when the function is equal to 12, is equal to the average, right? So f of x equals x squared equals the average value of the function from 0 to 6 at x equals 2 square roots of 3. Right? So I just added that in, not that it's a requirement, but on this particular problem, because it's our first problem with mean value theorem, just to give that a little context and have that make a little sense. Right? Let's go back and solve that other one back here. May as well find the when. And then I don't want this podcast to go too long. Let me see how many problems we have. We have 1, 2, 3. Enough for me to say, only 3, for me to say, let me make a second podcast and call it continued. But let's just solve this one real quickly. All right, it's because we already have it, we already know the what, right? The what, the average value here is 3. The when that would occur, if we set x squared equal to 3, right? Well, pretty easy to solve, huh? We get two answers, right? So x would equal positive and negative square root of 3. But one of them is no good because the interval is from 0 to 3, right? So x equals negative square root of 3. Negative square root of 3 is a no. It's outside interval. But x equals square root of 3, that is a yes. So this is the when, right? So at x equals the square root of 3, f of x equals the average value, I'll abbreviate, AV, average value of our function. Right? I'm going to end, and then I'm going to pick up with the last couple problems. Thanks for watching part 1. Part 2 is going to be a lot shorter. All right? Bye-bye for now.